Hey there, team. You ready for video number 5 for thermodynamics? So this is kind of an extension to the last two. I really could have done this one and the prior two all in one video, but I know our attention spans aren't an hour and a half anymore these days. Right? I can go about 10 minutes and I'm like, oh, butterfly. So I'm kind of splitting these up a little bit. So we looked at absolute entropy. We looked at entropy changes using Q reversibility over temperature. We looked at the three laws of thermodynamics. So now let's take one of those laws of thermodynamics, the third law, which gave us a zero reference point, right? A perfect pure crystal at 0 Kelvin has a zero entropy. And from that, we can get the absolute entropies or molar entropies if it's 1 mole of the substance at some specific temperature and tabulate those. So in Appendix D of your textbook or on a table that I have, so if you have printed out your thermodynamic tables, hey, double-sided, you'll see this on your exams. It's not a complete list in any way. This has a list of the molar entropies for different substances. So if you take a look at it, you saw this last semester where we had the enthalpy of formation, right? So we looked at that where you can calculate the heat of a reaction. And I gave you that equation by taking the products minus the reactants. And so those are your heats of standard heats of formation. Don't worry about the delta G. That's going to be Gibbs free energy later. But we're going to looking at the absolute molar entropy. See, joules per mole Kelvin. And so you just look up that particular element, look into the column with the biggest mistake is we picked the wrong column. You're looking for entropy and you end up doing the enthalpy. Like, darn it. So I got aluminum, barium, carbon, right? Different substances. So you can see all these entropies. Notice they're all positive values, right? You get a lot of zeros for the enthalpy and Gibbs free energy changes because by definition it's for forming an element, forming a substance from its elements in their standard states, which is if you're forming an element from its element in standard state, it's going to be zero. But since we're doing absolute entropies, those are going to be non-zero values. But the equations look identical, right? So using that first law of thermodynamics with that zero reference point, we can calculate the entropy change for a reaction. Now, from our table, we're limited to standard conditions. So on the next page, I'll review standard. Well, I might just talk about standard conditions because that's something we covered last semester. For any reaction, and we can bypass the Q reversible over T constraints. So that look familiar, right? So before we had delta H, the enthalpy change of a reaction, right, was the sum of the stoichiometric coefficient from the equation times the molar enthalpy of formation or standard heat of formation. A lot of people call enthalpy and heat the same thing. You'll hear me say those interchangeably. Of formation, and then you subtract, so it's your final state minus your initial state. So then you take the stoichiometric coefficient of the reactants times there, if it was the enthalpy, the standard enthalpy of formation. But for entropy, we don't need the delta S because of the third law of thermodynamics. We just need the absolute molar entropies. So just sum up the molar entropies from that table for each product multiplied by the coefficient. And some books use moles for that, some don't. So our textbook uses that as a unitless quantity. So we don't put moles on there. We just use a 2 or a 3 or a 1. Sum all those. So if you had 3 products, you'd take all 3 and add them together for that term. And then subtract the reactants, take the stoichiometric coefficient times whatever value you see in the appendix or on this table here, right? Just multiply them through and then add up all the different reactants and then take those terms, sum them all together, and then subtract them. Everything is decimal places here, so we will be limited by decimal places. It's effectively an addition subtraction problem. So limited by decimal places. So it makes it a little bit easier to track uncertainty because these stoichiometric coefficients are exact numbers. We don't have to worry about uncertainty with those. So it's in effect an addition and subtraction problem. So you can just bang your way through it. So just get this term, and then subtract those two terms limited by the fewest decimal places, realistically the largest absolute uncertainty. I will provide you this equation on exams, as well as all the other ones. You're going to have to think about thermodynamics. There's a whole bunch of equations. You just have to know, I said in the first video, what equation am I using and where's the negative sign go? That's how thermodynamics works. But the third law of thermodynamics gives us this nice little way of calculating entropy changes for reactions. But unfortunately, from our table, we are limited to standard conditions. That's what that little knot symbol means. So again, standard conditions, like if it's a substance, it's a pure substance, and it's like an element or something in its most stable state. So like carbon would be graphite, not diamond. Graphite's surprisingly the more stable state. That's why when you look in these tables for enthalpy, standard enthalpies of formation, graphite's 0 and diamond is not. Whoa, interesting, huh? Unfortunately, the kinetics of the diamond to graphite is a long time, longer than your lifetime, so you don't have to worry about your diamond ring turning into graphite anytime soon. But thermodynamically, that is a spontaneous process. All right, so we can run this pretty readily. Let's do an example problem just to show you how to look things up on the table and track our way through it. So let me throw a problem up on the board. If you don't have this table printed out from my website, go ahead and do that, or just look in the back of your book in the appendix and you can find these values. So I'll throw something up there, see if you can do it ahead of me. All right, team, let's see if you can bang this out. These problems are tedious, but very, very simple. What takes the most time on the exam is looking up the stupid values on the table. Right? Like, where is that stupid thing? So the more practice you can get with that, the better. You'll be quicker with it on an exam. It's just like when I coach softball or baseball. We practice so that you get the muscle memory for motions. You know what to do. You see a particular play develop, you know what to do. So like on an exam, you know it's this kind of problem. We're going to be having to use in the table. You know where to look. You're not looking in the wrong column or something by accident. You know immediately where to go. All right. So type of question you'll see on a quiz or exam. What is the entropy change for this reaction under standard conditions, right? If it was non-standard conditions, we wouldn't be able to use that table on the back of the book. And that's also, I think, for 25 degrees Celsius. So it's going to get more complicated when we're not at standard conditions and not at 25 degrees Celsius. There's going to be later videos for those. Yay! All right, anyway, well, how often are you under standard conditions? So let's take C3O2 gas. What is that? Carbon suboxide or something weird like that, some organic thing. Plus 2, so 1 mole of the C3O2 gas plus 2 moles of diatomic oxygen gas. So we're effectively combusting that carbon species, giving us 3 moles of carbon dioxide gas. All right, so we got a balanced equation there. Calculate this. So look up on your table, find the values for those 3 species, and then use that equation to pop it together. While you're doing that, I forgot to finish up the review, just to touch up on standard conditions again. Standard conditions, you're at 1 bar, approximately 1 atmosphere. Those are roughly the same within allowable experiment or error. So the pressure is 1 atmosphere, 1 bar. If it's a solution, usually it's a molarity of 1, technically an activity of 1. Again, a pure substance. Its most stable form at the temperature, specified temperature. So standard conditions don't really have anything to do about the temperature it's at. It's the conditions that are stated. All right, so look up those values. Let's write our equation and have at it. So we know that the change in that will be the sum, and I would give you these on the test, right? These equations of the products times their absolute molar entropies minus the reactants. And that little weird new symbol is the stoichiometric coefficient. So that would be the 1s, the 2, and the 3 up there. Oh, that's convenient. 1, 2, 3. All right. So pretty simple equation. Let's pop in. So our final state is our products over here. That's where the P and the P come from. So we're going to take 3, right? And our textbook doesn't use a unit of mole on that one, and it's an exact number. 3 times whatever the value is for CO2 gas. And if you look on here, the state makes a huge difference, all right? So for example, if you look on here, you can see under carbon, you see the C3O2, there's a gas in C3O2 liquid, right? Those are different values, right? So the C3O2 gas is 276.5 and the C3O2 liquid is 181.1. No big surprise, the liquid has a lower absolute entropy than the gas. Does that surprise you, right? So you have to have the state correct. You've gotta. Don't give me an equation without states because you're roast and toast, completely lost in thermodynamics. You have to know the states, because otherwise you don't know what value to use, right, gang? So do me a favor and look up these values for me, and then we'll write this down. All right, here we go. Let me get some purple here. So this is our final state. So we're going to take 3 times the value for the carbon dioxide gas. I was just there too. Oh, let's look this up. Carbon dioxide, I can't see very well. Looks like CO2 gas is right there. See that? CO2 gas. Going to the last column, 231.7. So it looks like 231.7. And look at the units, joules per mole Kelvin. So 231.7 joules per mole Kelvin. That will be our first term. And we only got one product, so we only have that one term. Now, I've seen books that use moles here. You take 3 moles, the moles cancel, and you end up with joules per Kelvin at the end, and then you just add moles to it per mole of reaction. Or if you do it like this, it leaves you as joules per mole Kelvin. So whether you do joules per Kelvin or joules per mole Kelvin at the end isn't critical. It's assumed 1 mole of reaction. All right? Always was a vague concept to me. So let's subtract, right? The reactants. So we have 2 reactants, so we're going to have 2 terms here. This is the same when we do enthalpies of reaction, right? Delta H reaction. It's the same equation. We're going to do the same thing for Gibbs free energy later, or Gibbs energy. The setup's exactly the same. You just use a different column on that handout. All right, we've got 1 mole of the C3O2 gas. Okay, so let's look up the C3O2 gas. Another carbon-based species. Oh, we looked at that earlier. Darn it, I should have wrote that down. So C3O2 gas, looks like it's right there. What did I say, carbon suboxide or something weird? Looks like a 276.5. Can you see that? Don't do the liquid, do the gas, 276.5. Let's write down 276.5 joules per mole Kelvin. Now, obviously on an exam, you're going to be moving a lot faster than I am now, because you're not talking to people or recording videos when you're taking the test. You're like, just whipping right through. All right? And this is a summation symbol, so I'm going to add the 2 moles of diatomic oxygen in the gas phase. So I'm going to put it on my 2 here. Let's look up the value for diatomic oxygen. So look under O for oxygen. Can you see? That's monatomic oxygen. So there's diatomic and triatomic ozone. We want O2 gas right there. Go across. Notice it's 0 for the enthalpy and 0 for the entropy. I mean the Gibbs free energy, which we'll do later. But we're going all the way to the end. 205.1 joules per mole Kelvin. 205.1 joules per mole Kelvin. Good thing I didn't have any more species. I'm out of board space. All right, so let's get your calculator. Calculate this term, the product term. Calculate this term. So take 1 times 276.5 plus 2 times 205.1. Good to 1 decimal. Give me that term. And then we'll subtract these 2. So it looks like everything's going to be good to 1 decimal place when we're done. All right, so 3, that's an exact number, times 231.7. What do you get? I think I got 695.1 joules per mole Kelvin. So that's the total molar entropy of all the products. Let's subtract the reactants. So 1 times the value for the carbon suboxide, 2 times the value for diatomic oxygen. Add them together, I get 686.7 joules per mole Kelvin. So now I can subtract these. So I got 1 decimal overall. Now let's see if we can predict this ahead of time. Remember, if you look at a reaction, you can kind of get a rough idea in most situations whether the entropy is going to be positive, the change is going to be positive or negative. Specifically, are you creating more moles of gas? Delta S would be positive. Or are you creating fewer moles of gas? Delta S would be negative. So let's look in here. So I got, these are all gas phase species. So I got 1 here and 2. So I got 3 moles of gas on my reactant side. Ah, crud monkeys. I got 3 moles of gas on the other side. There goes that theory. We can look at the complexity of the molecules, right? That's our most complex molecule, C3O2, but O2 is our least complex. CO2 is kind of in the middle. So you got 3 atoms here. You got the 2, it's carbon-oxygen double bonds vibrating. You got the O2 with just the one double bond, and then the C3O2 with a whole bunch. So you've got 3 intermediate complexity on one side, 2 low complexity and 1 high complexity. That's indeterminate, man. I'm looking at that. I couldn't tell you if delta S would be positive or negative. Too challenging to look at qualitatively, but my guess is it's not going to be high on either extreme. It's probably not going to be a really high positive delta S. Probably not going to be a very high negative delta S either. It's going to be close to 1-ish. We'll see. Let's take, and it looks like it. Let's take that minus that. I get 8.4, my friends. 8.4 joules per mole Kelvin. There is no non-rounded value there. And in a lot of books, you'll see that as 8.4 joules per Kelvin as well. It's per molar reactant. So that kind of makes sense, right? It's not far off from 1. It looks like that is a favorable process entropically. But we couldn't have really nailed that without the numbers to it. So this is a much better way of calculating entropy changes versus the other way we showed you with the Q reversible over the temperature. This will be our method of action unless we're doing phase changes or calculating boiling points or something like that. Sweet. Next video, we're going to get into using the second law of thermodynamics and we're going to take the enthalpy and the entropy together.